Okay, yeah, so thanks again so much for organizing the meeting and for everyone coming. So I'll basically mainly talk about a few of our recent works on really trying to extend ideas from heterostructure engineering of twisted bilayers or multi-layers to materials beyond graphene. So the basic idea and the premise for what we would like to do is really try and find new materials platforms beyond graphene of particular compositions of different heterostructures that can be used to simulate paradigmatic quantum Hamiltonians and perhaps explore regimes that are not readily accessible in the solid, in the sense that they constitute a particular regime of parameters that would be considered extreme for regular kinetic energy scales in a solid, but can actually arise quite naturally at a twist in tailored heterostructures. Okay, well, I guess this doesn't really need much introduction for this meeting. But the basic idea really is just a question of extending the paradigm set by twisted bilayer graphene, where it was shown that at small twist angles, particularly around magic angles, the superlattice potential or interference in the superlattice potential acts as a knob to quench the kinetic energy scale and instead really bring interaction mediated physics to the forefront. So in graphene, of course, this led to well-known observations of correlated insulating states as well as superconductivity as a function of filling, which is also finely tunable in these heterostructures via gate control. And this has really been extended to a variety of graphene systems, namely not just bilayers, but trilayers or bi-bilayers in various experimental groups. But sort of a broader perspective on this is to ask whether this very same physics can also generalize to materials away from graphene. In particular, other van der Waals materials, such as transition metal dichalcogonite, mono and multi-layers. So again, the idea is, well, you start with a material where the intrinsic kinetic energy scale is at a fairly high energy scale that's going to be EVs. However, as you compose multiple layers and stack them at a twist, the question is whether this paradigm of quenching the kinetic energy scale can bring other competing effects to the forefront. So this now has been extended in various ways by various groups. In particular, there's been a lot of experimental efforts on the 2H transition metal dichalcogonite multi-layers at a twist. For instance, twisted tungsten diselenide or tungsten disulfide, where one starts from a semiconducting monolayer and then essentially builds a Lego construction, which is of layering these materials on top of each other at a twist, and finds that while there are no magic angles, unlike graphene, which is a property that is very unique to Dirac semi-metals at a twist, one nevertheless finds a twist angle reduced kinetic energy scale that leads to quasi-flat Moiré bands at the top of the original valence band, which, if one can gate into them, can realize, again, a variety of correlated insulating states and other interesting states of matter. So, however, this is not the end of the story, because really there's more aspects or more parameters in a material that one could think about controlling and really make become a dominant energy scale at low energies. So on one hand, an open question is the question of dimensionality. So heterostructures by design are essentially two-dimensional. However, one can ask whether one can go slightly beyond this. Particularly, one can either ask about dimensional reduction, namely starting from a two-dimensional heterostructure, and asking whether twist angle gives a way to reduce dimensions from 2D to 1D in a controlled manner. This relates to recent work by the Vishwanath group and us with proposals in germanium selenide and other rectangular Bravais lattices, where the idea is to exploit anisotropy of the original monolayer to quench the kinetic energy scale in only one of the two spatial directions. However, one can also ask whether one can go in the opposite direction, namely start from a two-dimensional twisted heterostructure and really think about this as a building block to build a three-dimensional crystal. And with the advances in experimental composition of these heterostructures, this is now within reach. And actually, sort of simple examples of this have already been demonstrated. So one can ask whether one can take a twisted heterostructure as an ingredient and build a three-dimensional material that nevertheless allows for twist control of the complete three-dimensional band structure. So I'll talk about an example of this a little bit with another recent proposal from the Sarma group. Finally, one can ask about the intrinsic orbitals that arise in the Moiré heterostructure. As one twists at small twist angles, one can think about the effective low energy structure again to arise in terms of effective orbitals that form in the Moiré supercell. And one can inquire whether a twist angle gives a way to change the orbital anisotropy and composition of these orbitals to engineer some interesting effects. And finally, but actually very interestingly, so far the role of spin-orbit coupling has pretty much been neglected in the sense that one missing ingredient of quenching the kinetic energy scale really is the possibility to potentially quench the kinetic energy scale in such a manner that the spin-orbit coupling becomes the dominant energy scale at low energies. And that's a very exotic regime compared to a regular material, but has very interesting implications on the topology of the bands that arise and the role of interplay of topology and correlations. So for the remainder of the talk, I'll give three examples on the right. Namely, I'll talk about the 2D to 3D crossover from a controlled stacking of heterostructures. I'll talk about orbital anisotropy that can arise in a very simple example in twisted MOS2. And I'll talk about the role of spin-orbit coupling in work that's currently in preparation for twisted group 4 transition metal dichromate nets. So to start, really the basic premise is to ask whether one can use Moiré heterostructures as quantum simulators. And by that we mean that can we use a heterostructure, whether the fine control that the heterostructure allows, to engineer tailored states of matter. Sort of the elementary question is the realization of various lattice models, which is hand-wavingly shown in this figure taken from a recent perspective article by some of us at CCQ, as well as Columbia and the Max Planck Institute. So one can think about engineering triangular or hexagonal lattice systems, but also rectangular lattices that ultimately give way to one-dimensionality at certain twist angles. And one can then ask as a follow-up question whether the particular orbital structure and this effectively engineered Moiré lattice gives access to new states of matter. For instance, quantum spin liquid behavior, unconventional magnetism, unconventional superconductivity, excitons, or even extending such ideas to already intrinsically correlated monolayers and stacking them at a twist. So the first example that I'd like to give is comes for twisted bilayer MOS2. So this work was done together with Dominique Kiese, Michael Scherer, and Simon Trebst at the University of Cologne, and Lede Sian and Angelo Rubio at the Max Planck Institute, as well as Dante Kennis in Aachen. And in particular, this work is motivated by the observation that if we look at the untwisted bilayer of transition metal dichalcogenites in the 2H structural phase, so trigonal prismatic coordination, then there's actually two classes of untwisted bilayers. So on one hand, one can have the situation where the valence band maximum lies at gamma, with the valley valence band, the second valence band maximum at K, being at a significantly lower energy detuned from the gamma point. This is the case for MOS2 as well as MOSE2. And you could have the alternative case where the valence band maximum is nearly degenerate with the the K point is nearly degenerate with the valence band maximum at the gamma point. That would be the case for twisted tungsten diselenide. So in the former case, if the valence band maximum lies at the gamma point, and one now imagines going to very small twist angles, so this is recent work by us and also a proposal by Alan McDonald's group, just published this year. One can imagine at very small twist angles that in fact the states at the valleys should not really play a role for the low energy behavior at small twist angles at the top of the original valence band. So instead, really the highest Moiré valence mini bands should be composed solely from the dz squared orbitals at the gamma point, which lends itself to an extremely simple picture. So we can think about this untwisted heterostructure and then stacking two changing twist light twist angle, which effectively engineers through the repeated misalignment of the two layers, the periodic misalignment of the two layers, to essentially asking about the combined dynamics of essentially a free electron gas of molybdenum dz² orbitals in a long wavelength Moiré potential that has the appropriate symmetries of the lattice. And in particular, if I'm looking at the very top of the valence band of MOS2, I will have almost perfect six-fold rotation symmetry, even though in the twisted heterostructure, of course, my symmetry is reduced quite drastically. So I can really think of this problem as sort of a scalar potential on top of a free electron gas. And that already gives us a route for doing more interesting things, because we could also ask, well, what happens when you have more bands, and what happens when the potential is not scalar anymore, but you have a matrix valued or non-abelian potential. But let's first think about the scalar potential case. And in fact, this was proposed already quite a while ago in the context of cold atoms, where the realization really is just with the Moiré potential being replaced by an optical lattice. So if I think about, so this is a lattice regularization of really a continuum model, how the bands that arise under this long wavelength Moiré potential, as I increase the potential strength, what I will find is that this potential essentially forms minima that form a honeycomb lattice in the plane. So I will form orbitals or charge puddles that will be localized at the honeycomb sites of this potential, which forms a series of Moiré mini-bands, notably at the top, just a regular honeycomb lattice of Moiré S orbitals. But what's more interesting is if I go to stronger Moiré potentials, I can ask about the subsequent next orbital sets of orbitals that form in these locations. And it turns out the next set of orbitals will be two orbitals of px and py character, again localized at these honeycomb lattice position minimas of your Moiré superlattice potential. And this now constitutes essentially a px-py honeycomb lattice model. However, with the orbital anisotropy now being a function of the twist angle, as I'll show in a second. And even more interestingly, if you go to even stronger Moiré superlattice potentials, it turns out the next set of bands actually forms a Kagome lattice of Moiré S orbitals at the shoulders of this. Can you see my mouse cursor? Okay, great. At the shoulders of this potential here. However, in practice, of course, this is just a toy continuum model to understand the effective physics. So we really need to ask, using large-scale ab initio simulations that account for lattice relaxations, how realistic these effects are. And so, in fact, it's exactly what we did, or particularly what Leda did, using really heroically large-scale simulations with thousands of atoms in the unit cell, to study under full relaxation how the ab initio structure of such a large supercell looks like. This is 3 representative twist angles for bilayer MOS2 at a twist. And again, in ab initio, we see nicely this honeycomb lattice s orbital bands arising at the top of the band gap, with now the next set of bands becoming progressively more isolated as I go to lower twist angles, and thereby essentially enhance the role of the Moiré potential, giving me a second set of bands that form precisely this honeycomb lattice of px and py orbitals. So what does that mean in terms of an effective model? Now, these are, of course, MeV energy scales, or tens of MeVs. So I can, in principle, gate tune such that the chemical potential lies not in the topmost set of s orbitals, but instead the px-py orbitals. And if I constrain myself only to that band, a simple anisotropic px and py model can be fitted to the ab initio structure, and gives the interesting result that actually, the nearest neighbor type binding model will just be parametrized by pi and sigma hopping between the p orbitals. And the relative magnitude of pi and sigma orbitals, which correspond to the essentially shape of the Moiré orbitals, is a function of sigma hopping, of twist angle, becoming progressively more anisotropic as I decrease the twist angle, in addition to the bandwidth. So this inset here is the ratio of pi hopping versus sigma hopping, decreasing as a function of twist angle, whereas the outer subplot is the bandwidth of the set of bands, which is also reduced due to quenching of the kinetic energy scales. So this gives a route for 2 things. So first, I can tune the anisotropy. And second, the peculiarity about this PX-PY model in the anisotropic limit is the emergence of an almost perfectly dispersionless band, which now doesn't arise due to a magic angle condition, but instead really arises due to kinetic interference, very similar to a flat band in a Kagome lattice or a Lieb lattice. So this manifests itself in terms of a peak in the density of states, and we can already expect that correlated, the role of electron interactions will be prominent as we dope into these bands. So let's just briefly chat about the interacting phases that this model permits. So calculation of interaction parameters, unfortunately, is out of reach for ab initio simulations with thousands of atoms in the unit cell. In principle, one should be scaling things like constrained RPA with recent efforts in theoretical groups listed here. Instead, we'll take the perspective that we'll just take a local interacting model of Hubbard-Kanamori type and treat our interaction parameters as free parameters. So in particular, we'll focus on the quarter-filled case, since this is a 2-orbital model. Spin orbital physics at strong interactions might be quite interesting. So at quarter filling, it turns out as a function of U, already for one finds an interaction-induced metal insulator transition with the charge degrees of freedom becoming inert for U greater than U or T greater than 4. So if that is the case, we can ask, well, can we devise an effective model for the low energy spin and orbital dynamics, where at quarter filling now we have both the spin of our electrons plus the orbital px or py component, which just amounts to essentially a twist-tunable anisotropic Kukulkomsky model. So this physics is in principle very similar to the case of twisted bilayer graphene, where you also have a px-py model. However, now with the crucial difference that the anisotropy, i.e. the ratio of sigma and pi hopping, which manifests itself in anisotropy in the Kukulkomsky model, is now a function of twist angle. And then the right is a phase diagram calculated in mean field theory, showing a variety of anti-ferromagnetic phases with nematic orbital orders, with ferroorbital or anti-ferroorbital nematic order as a function of interaction parameters.
Martin, can I ask a question?
Yep.
This is Lucas. Just why are there no like longer range density interactions? Is there a reason you can rule them out? Or as far as I know, in TBG, they're quite significant, or they're quite important, right? So
that's an approximation. So first,
would something change in these phase diagrams, or do you expect something significant to change significantly?
So if you so there's a 2-step procedure here. So first, longer ranged interactions are dropped here out of simplicity because we don't know how to calculate these interaction parameters. But that being said, of course, the distance between the Moiré orbitals is very large at small twist angles, such that one could imagine that these interactions might can be suppressed at very small twist angles. Now you could ask about how well is the bare interaction screened, and this is really a question that would have to be solved in constrained RPA calculations. However,
could you remind me how this Could you remind me how this in twisted bilayer graphene is? Have people looked at like next nearest neighbor density and so on?
So twisted bilayer graphene is a little trickier because of the shape of the orbitals. So this relates also to the topological obstruction that the model has. So this is not the case here, since you start.
Okay, yeah, that makes much more sense now. Okay. Yeah.
Actually, yeah, that's an important point.
I also have a question. Sorry. It's like since this is a honeycomb lattice and it has some anisotropy, so could we relate it to some spin liquid phase like the K-type spin liquid?
So if related to a K-type spin liquid, so first of all, this is this analysis here is for the quarter filled case for a spin orbital model. So you could to get a K-type like spin liquid phase, or at least the simplest realizations, you would want a spin 1/2 moment. However, you need bond dependent, highly anisotropic easing-like interactions, which means you need a strong spin orbit coupling component. And MOS2, while in principle, let me just go back here. MOS2, oh, too far. MOS2 does have strong spin-orbit coupling, but it does have strong spin-orbit coupling at the K point. So the twisted states are dominated by the gamma point, which by symmetry doesn't have no spin-orbit coupling because it's just a dz squared orbital with a strong detuning to the lower lying bands of different character. So actually spin-orbit coupling in this compound doesn't play a role. But I'll show in a second an example where spin-orbit coupling becomes very important. Furthermore, actually, to realize Kitaev-like physics, to get this bond dependence, really what you'd want is something analogous to sort of a T2G3 orbital model instead of a PXPY model.
Thank you.
Oh, and just for Lucas's question, yeah, so of course we've neglected longer range interactions, and there's partially because we don't have to deal with the topological obstruction that graphene has. But in principle, as the charge gap opens at a given local Coulomb repulsion, the Kugel-Komsky physics will likely be, so essentially this will just be a small modification of the effective Kugel-Komsky exchange parameters, which are not shown here as a function of longer range interactions. Okay, so actually now going forward regarding spin-orbit coupling, so all of these considerations really regarded group 6 TMDs. So this regarded twisted MOS2, but in principle also MOSE2 or tungsten disulfide. However, one can also ask whether one could play similar games with other TMDs. And very prominently, one could look at the group 4 TMDs, such as twisted zirconium disulfide or twisted hafnium disulfide. Which in the monolayer and in the untwisted bilayer are already pretty well characterized, but which have the important difference that while the group 6 TMDs naturally want to crystallize in the 2H phase, so with trigonal prismatic distortion coordination, group 4 TMDs can crystallize in a 1T phase with octahedral coordination. And I'll show how actually this means that spin-orbit coupling really plays a central role in these considerations. So this work is again with Leda, Dante, and Angel. And really the premise is to look at the 1T structure of a zirconium disulfide monolayer and note that the valence band maximum, so this is again a semiconductor of like an EV and something of a band gap, and the valence band maximum is now not composed of a DZ squared transition metal orbital, but instead the PX and PY orbitals of sulfur of the van der Waals layer. And notably, in the absence of spin-orbit coupling, these two orbitals would be degenerate. However, strong spin-orbit coupling already in the monolayer now breaks this degeneracy and introduces a finite spin-orbit coupling at the gamma point. So now we could think about the same situation and ask, well, what if I take, so this is the bilayer band structure actually, without twist. If I now impose a small twist angle, again, I would expect that since this is half an EVD tuning to the next valence band, second valence band maximum here, that at small twist angles, all physics will be dominated by the PX-PY orbitals plus spin-orbit coupling at the gamma point. However, the situation is now a little more involved because I have not one, but two orbitals. So if I want to build in the Moiré supercell, so this is just showing the different alignments of the two layers across a commensurate supercell. If I again want to build an effective continuum model to describe the effective Moiré bands that emerge from treating the electrons here as essentially free electrons, but now with a two orbital PX-PY character, plus a Moiré superpotential, I have to be very careful because first, I have to make sure to properly account for the PX-PY character in the kinetic term. However, crucially, the Moiré potential will now not be a scalar, but will be a matrix valued potential. And finally, I should expect a L dot S like spin orbit term that will, as we'll see, will dominate at low energies. Particularly this matrix valued spin Moiré potential, again, using the same considerations as in MOS2, if I look at the very top of the valence band, my bands will, even though, of course, the heterostructure is chiral, the highest bands will be almost C6 and symmetric with mirror symmetry, which poses strong constraints from these symmetries on the form of the Moiré potential. In fact, one can show that this Moiré potential really only has two free parameters, namely a scalar potential, just like before, plus a matrix valued potential term that admixes the px and py orbitals. So taken together, what does that mean for the low energy structure at the top of the original valence band? So again, I can first ask, well, what happens if I just consider the scalar potential and ignore spin orbit coupling for now? So my px, py orbitals are degenerate at the gamma point. So at very small twist angles, this is just the folded supercell. And as I increase the value of the scalar potential, I progressively, again, localize electrons at the minima of the honeycomb lattice in the superlattice potential. However, now not with s orbital character, but again with px, py orbital character, since I started with px, py orbitals. So there won't be an s orbital honeycomb lattice, unlike MOS2. Instead, the highest set of valence bands is now of px, py character on the honeycomb lattice, again giving this 4-band dispersion with a quasi-flat band. However, that ignores the matrix value part of the potential. And if I look at the orbital character, so these are density plots at the gamma point of the charge density distribution in the supercell. So the top 2 bands are just, or the top 4 bands are just localized at the honeycomb sites in the Moiré superlattice potential. But if I look at the 5th band from the top, I already find that actually this 5th band has Kagome characters instead localized at the shoulders of the original Moiré potential. So now we can ask, well, actually, does this give us an angle to make these bands become the dominant bands and push them to higher energy? And indeed, that's exactly what the matrix valued component of the Moiré potential does. So now if I think about starting with a scalar potential and increasing the magnitude of the matrix valued potential, now as I increase, I shift up the Kagome band, shift down the lowest band of the 4 px-py bands, and finally emerge with a well-resolved, energetically separated structure of 3 Kagome bands, which are now localized, which are s-orbital-like and localized on the Kagome sites in this effective Moiré triangular lattice structure, and are energetically isolated from all lower-lying bands as I go to very small twist angles, hence larger Moiré superlattice potential. Now, to compare this with ab initio results, this is, again, large-scale, extremely difficult to compute ab initio results for thousands of atoms in a supercell, going from 3 degrees down to 2.28 degrees as the maximum we can reach without spin-orbit coupling. And you see precisely this pattern. So at large angles, you have this flat band at the top that originates from the px-py bands. And as you decrease the twist angle, gradually a set of Kagome bands emerges to the top that, unfortunately for the twist angles that we can reach, is still not fully separated from lower lying bands in the superlattice. However, we also observe, again, effectively linear scaling of the total bandwidth of these Kagome bands with lowering twist angle, as well as band separation to other bands. So just to show how the charge density for this looks like, to see that this is actually a Kagome lattice, again, at the gamma point, we find precisely for these bands and these bands, so this is shown for 2.64 degrees, a Kagome structure of charge density, and with the intervening bands having sort of a ring-shaped charge density structure that is localized in the center of the hexagons of the Kagome lattice, which should be shifted to lower energies. In fact, we can model this behavior just very simply from our continuum model, which shows precisely the same physics at weaker Moiré potential, where you form a Kagome lattice that is not fully separated from these ring-shaped orbitals that are localized at the center of the hexagons. So now this ignored spin-orbit coupling, but the role of spin-orbit coupling is very simple to see. So this will just, by symmetry, necessarily break the degeneracy that's at the Dirac points and the Kagome structure at K, as well as lift the degeneracy at the gamma point between the flat band and the dispersive Kagome band, leaving 3 energetically isolated bands, here shown for twist angle 2.45. Actually, sorry, these twist angles are not the same. This is the lowest twist angle we can get for spin-orbit coupling, which is a slightly more expensive calculation. Giving energetically isolated bands, with now spin-orbit coupling really becoming the dominant energy scale. So all of this, the gap between these bands is set purely by the strength of the L.S local spin-orbit scale, which now competes with the quenched kinetic energy scale and hence really becomes the dominant contribution for the highest Moiré bands at low, small twist angles. So two things that are important about this. First, these bands are topologically non-trivial. Those are actually spin churn bands. And really this gives us a route towards tuning into the ultra strong spin-orbit coupling regime, where the dominant scale becomes spin-orbit coupling. To see the topology, let's try and devise an effective model for the cargo med lattice. So essentially this just amounts to building a tight binding model for orbitals localized at these sites here and these charge puddles. And the minimal model amounts to having nearest neighbor hopping, which is both real and has an imaginary part, which comes from spin-orbit coupling, as well as to properly fit the low energy band structure. You also need to account second and third nearest neighbor hopping. And already foreshadowing what we're going to do, we're also going to ask, well, now what happens when you add interactions, namely in the simplest case, just a local Coulomb repulsion plus a nearest neighbor Coulomb repulsion. So the salient things are this model models a time reversal invariant flat band quantum spin Hall insulator. The bandwidth is again twist tunable, and in particular the spin orbit coupling. So this is just from the fitted points for the angles that we simulated in ab initio. This is the ratio of spin orbit coupling over the nearest neighbor kinetic hopping, which is the largest kinetic energy scale. As one decreases the twist angle, one increases this ratio, providing monotonic tuning into, well, not quite monotonic tuning, but into the strong spin orbit coupling regime. Why is this interesting? Well, as these bands are now substantially separated energetically, we can think about gating such a device such that the chemical potential is shifted into the topmost Moiré almost flat band that emerges from this cargo med structure after spin orbit coupling, with the band gap here set by spin orbit coupling. And if this band gap is large enough, then the lower lying bands will effectively remain inert. So these bands will be fully filled, and we can really inquire about the role of interactions in a partially filled, topologically non-trivial time reversal invariant band as a function of filling fraction tunable via gating. So these bands have spin churn number plus minus 1, the top band and the bottom band in the cargo med lattice, actually, with the middle band being trivial. And this lends itself to a very neat analogy to a simple picture with Landau levels. So if this is a topological band, which is almost flat and has a non-zero spin churn number, that is essentially analogous to asking about a model of Landau levels for spinful electrons now, where the direction of the magnetic field is reversed for the two spin components, hence preserving overall time reversal symmetry. So actually, this was first proposed by, studying problems like this was first proposed by Shucheng Zhang's group at Stanford, where now the idea is if the cyclotron frequency is large enough, with the cyclotron frequency in our picture being the energetic separation to the other bands, then electrons will be confined to to Landau levels, which amount to a churn number equals 1 band, with equal and opposite chirality for the two spin orientations. So we can, armed with this, we can study this problem quite analogous to how one studies fractional quantum Hall physics. Namely, a minimal model should just consider the topmost band at fractional filling and ignore the inert bands, which amounts to a lowest Landau level-like projection, but now for spin churn bands, effectively ending up with one weakly dispersing band. This is now the dispersion of the topmost cargo med band, plus a projected interaction that accounts for all of the effects of topology through a projection in terms of the Bloch wave functions given with orbital indices alpha here. Notably, since all of the topology is encoded in the interaction, the fact that the spin churn number is non-trivial means that there is a topological obstruction to forming a simple tight binding model-like description of the interacting physics. This is a Wannier obstruction to the formation of localized orbitals. So if I wanted to represent interactions in this band in a real space picture, my interaction would necessarily be long range because the orbitals that I would have to form would not be able to be localized exponentially. Instead, would have a power law tail leading to long range interactions. That's analogous to the essence of a Landau level preventing a localized crystalline basis. So now let's first think about the half-filled case in this system. So if I fill the spin turn band at half filling and the dispersion is sufficiently weak at small twist angles, then essentially what we find is a ferromagnetic instability as the local Coulomb repulsion, or actually interestingly also parametrized by nearest neighbor Coulomb repulsion here as an additional parameter, reaches order of the electronic bandwidth of this topmost band. So this is really somewhat analogous to flat band ferromagnetism originally proposed by Mielke and Tasaki, or also quantum Hall ferromagnetism in multi-component quantum Hall systems at commensurate filling. And in particular, we find that as one exceeds a critical interaction strength, which amounts to the bandwidth of the topmost band, one spin polarizes the electrons, which amounts to filling one of the two term bands and gives a correlation-induced quantum anomalous Hall effect, which is a gapped system with a gap that again scales with the strength of the interactions. Now, it's very useful to compare this to the case of twisted bilayer graphene, because we now have experimental observations from numerous groups for a quantum anomalous Hall effect in TBG. However, the quantum anomalous Hall effect there is much more involved in the sense that it doesn't happen at half filling. Instead, you have to go to a nu equals 3 filling fraction, with nu equals 4 being fully filled. And the quantum anomalous Hall effect then really arises from a subtle interplay of the fact that the valleys are topologically non-trivial, or well, you can assign a valley Chern number to each of the valleys. And interactions drive the system into a spin and valley polarized phase, triggering a transition to a quantum anomalous Hall insulator. So that's one of the one of the expected theories of this effect. Here, the systematics is significantly simpler and really relies on flat band ferromagnetism. So we're at commensurate filling, in particular half filling. In principle, one can also imagine something similar happen at quarter filling. Essentially, the transition to the quantum anomalous Hall insulator amounts to interactions exceeding the bandwidth analogous to a Mott transition, where the system can spontaneously lower its energy just by completely polarizing its spins, and thereby paying 0 interaction penalty due to a local Hubbard interaction, which gives you a penalty for having a spin up and spin down. This really is a much simpler mechanism of creating an interaction-induced ferromagnetic topologically non-trivial state. So a natural follow-up question to ask is, well, what happens if one goes away from half filling and goes to fractional filling? So this question of fractional topological insulators, or more precisely fractional Chern insulators, as the sort of fractional quantum Hall analogy in lattices with non-trivial Chern number to a fractional quantum Hall effect in the Landau level, already has a number of proposals in the context of TBG, in particular twisted bilayer graphene, but also heterostructures of twisted HBN on trilayer graphene or double bilayer graphene, where the idea now is to essentially make an assumption that if the spin valley polarization persists as one dopes away from commensurate filling, then at fractional filling of the resulting Chern bands, if the interplay of interactions allows, one can think about condensing into a abelian-Laughlin-like state, or even high-order composite fermion-like states. The basic idea is, or the basic understanding of this really comes about from a mutatis mutandis mapping between a quasi-flat band with non-zero Chern number and a Landau level. But the key obstacle is that the spin valley polarization must persist at fractional filling. So zirconium disulfide in this sense is a very useful alternative in the sense that the ferromagnetic state arises not from spin valley polarization, but just from the fact that in any flat band for sufficiently strong interactions, you will form a ferromagnetic state, giving you an easier route to realize an isolated Chern band. So to assess how this works in a little more detail, we looked at the fractional quantum Hall effect at 1/6 overall filling, which corresponds after spontaneous time reversal symmetry breaking to 1/3 filling fraction for spin polarized electrons. So on the left is shown a plot of magnetization as a function of local Coulomb repulsion U and nearest neighbor Coulomb repulsion U prime, showing just the magnetization. And one finds even at fractional, so at this fractional filling away from commensurability, again, for local Coulomb repulsion on the order of the electronic bandwidth, one finds a transition to a spontaneously spin polarized ferromagnetic state. So this is a robust ferromagnetic transition for U greater than the electronic bandwidth. However, now if these electrons are fully spin polarized, any organization of the spin polarized electrons must necessarily come about from an interplay of the dispersion, that is of course not zero, and longer range interaction. So that's where the role of U prime, the nearest neighbor interaction, comes in. And it turns out that as one increases U prime beyond the critical value of U prime, one finds a transition to an incompressible state, which obeys, so this is a simulation and exact diagonalization, parametrized in terms of total crystal momentum versus energy of individual lowest lying excitations above the ground state, giving beyond the critical interaction strength exactly a threefold ground state degeneracy that's expected for a nu equals 1/3 Laughlin state. And in fact, we can probe this in a little more carefully, for instance, by asking about the flow of the ground state degeneracy under flux insertion through handles of the torus in periodic boundary conditions, matching, in addition to the momentum counting following sort of a generalized Pauli principle for fractional Chern insulators, exactly what is expected for a nu equals 1/3 Laughlin state from now a strong nearest neighbor interaction. So actually, how long is this? How much time do we have left?
Well, you started at 11:30, I mean, or later, so at least 12:30, but we've also blocked it till 1, so at least 10 minutes, but if you want to go longer, then go longer.
Okay, perfect. So then I'll briefly discuss sort of the last point of trying to extend heterostructure engineering beyond 2 dimensions. And the basic idea is now that if we can take twist angles between successive layers, can we use a similar idea to engineer dispersions out of plane? Now, naively, if I just think about a chirally twisted structure, I will naively break Bloch's theorem such that I can't define a simple commensurate supercell anymore. Instead, a very simple generalization of twisting to 3 dimensions is thinking about twisted sets of layers that one progressively stacks on top of each other. The simplest realization of this is shown here. So let's just think about sets of 2 twisted layers that are at a small twist angle and just stack them on top of each other to form a 3-dimensional material. So now if I consider the single twisted single twisted bilayer and think about where my charge density is localized. So this will be forming some lattice of puddles of charge density, say a honeycomb lattice or a Kagome lattice. And I stack these layers on top of each other. Now, twisting will progressively quench the dispersion in the plane. So this is this essentially flattened line given by example here for HBN. However, in the 3rd dimension, these charge puddles essentially align in the out-of-plane direction, still allowing electrons to hop with basically unchanged magnitude out of plane, leaving significant dispersion in the out-of-plane direction. So really, this scenario we can think about as a 3D generalization of a wire model of twist-tunable in-plane band flattening, however, still having a remaining dispersion on the z direction, which is interesting in itself, but does not amount to twist control over all 3 directions. So an alternative, of course, would be to just introduce spacer layers between subsequent layers. So think about pairs of twisted layers, then introduce a spacer layer, add another pair of twisted layers. this will progressively quench the out-of-plane dispersion and certainly eventually lead to a band that is flat in all 3 dimensions by virtue of being decoupled in the 3rd dimension. However, a caveat for our purposes is that this really does not afford twist angle control of the 3rd dimension. So this is instead a materials composition control of adjusting the number of spacer layers, and also comes with difficulties of aligning the pairs of twisted layers across the spacer layer to form an aligned stack of 3-dimensional twisted layers. So the 3rd scenario that we can think of is, for lack of a better word, a twist on the previous examples. We can think about taking our fundamental cell not to be single monolayers that we stack at a twist, but instead twisted bilayers. So now what happens with twisted bilayers is that if I orient my 2 layers in such a way that the natural stacking is sort of at a twist from, say, AB Bernal stacking for graphene, then I can geometrically engineer my stack of 3D twisting in such a way that the charge puddles in my twisted bilayers are going to be localized on 2 sides, for instance, the 2 honeycomb sides of the lattice, but with the 2 honeycomb sides being localized in different layers of subsequent of the 2 bilayers which form my elementary cell, such that if I now combine sort of sets of these bilayers at a twist, I get strong coupling between these charge puddles, but the distance between neighboring charge puddles across the stacks will now be a function of twist angle, as well as the in-plane dispersion will be a function of twist angle, giving me an angle to, well, again, for lack of a better word, by twisting, by changing the twist angle, to change not only the in-plane dispersion, but also by virtue of separating subsequent locations of the charge puddles to quench the out-of-plane hopping, really giving twist angle control of dispersion in all 3 dimensions. So from this very simple picture, how this works in practice is shown here by the example of twisted hexagonal boron nitride as well as a well-controlled example of these ideas. But really, I want to emphasize that this strategy is in principle very generic. So this could be done with any possible van der Waals material, which allows for composing subsequent stacks of bilayers at a twist with charge puddles being placed at inequivalent sites in the plane. So the effective low energy physics is shown here with the bands on the right as a function of decreasing twist angle, essentially being composed again of these charge puddles, which now form a honeycomb lattice in the plane. However, with the 2 sides of the honeycomb lattice being in different layers of my pairs of layers. So this amounts to first being able to use twist angle to quench in-plane hoppings T1 and T2 as a function of changing the supercell side and moving these charge puddles away from each other. And finally, also allowing changing of the out-of-plane T3 dispersion that gives me hopping between the layers, since these charge puddles are now spatially separated between alternating layers. Giving a way of, so this is the band structure with the in-plane direction being shown from the center axis gamma to gamma here and the out-of-plane here, giving a way by reducing twist angle to progressively quench all 3 directions of the band structure simultaneously. In this case, again, forming a honeycomb lattice of these charge puddles, with the 3rd direction being quenched simultaneously with the in-plane direction. So these are, again, ab initio simulations for the periodic structure at commensurate angles. And I think an easy way to see the effective physics is this top-down view here, which just shows where the charge puddles are localized. From the top-down view, they form a honeycomb lattice. From the side view, however, you see that inequivalent sites in the honeycomb unit cell occupy different layers, giving rise to the out-of-plane twist control of the dispersion. So armed with this band structure, we can ask sort of the natural follow-up question, presuming that we can dope into these twisted flat bands, which of course in the three-dimensional case is a different challenge than the two-dimensional case. And skating doesn't readily translate, but one can think about chemical doping. Then we can ask about now instabilities not in the two-dimensional flat band, but in the full three-dimensional twist-controlled, almost dispersionless band. So to see this, first the top is showing a set of magnetic instabilities calculated in random phase approximation via tuning of the chemical potential in the honeycomb lattice bands, so as a function of filling. Half filling again, since this is an approximately bipartite lattice, given our fitting of the ab initio data, one gets the usual antiferromagnetic order. Now in the random phase approximation, as one goes away from half filling and one goes to an almost filled band, one gets a ferromagnetic instability, a dilute electron or hole doping. Whereas in the intervening regions for finite filling, however, for a pretty large critical U, one finds competing spin density wave instabilities at finite ordering vector Q, which is shown schematically here on the right, giving rise to a variety of different magnetic ordering patterns. So the more interesting thing actually is, since these instabilities are the pretty large critical U, we can ask about, well, what happens at lower U, where fluctuations of the magnetic order can still dress your effective interactions and give rise to an effective superconducting instability from originally repulsive interactions. So this is shown on the bottom here for a very small doping of a few MeV away from half filling from the antiferromagnetic phase, showing still almost perfectly nested Fermi surfaces in the third dimension, leading to large spin fluctuations with wave vector Q alpha, which now, under studying the superconducting instabilities of the effective fluctuation renormalized interaction vertex, gives rise, can trigger competing instabilities in the D wave, P wave, or F wave channel. And in fact, we find a dominant instability in the DXZ and DYZ channel, which are degenerate under the threefold rotation symmetry of the lattice. And hence, via a simple Ginzburg-Landau analysis, in fact, forms a time reversal symmetry breaking superconducting instability, analogous to what's been proposed by some groups for twisted bilayer graphene in 2 dimensions. So I should say this is not a topological superconductor, since this is still nodal in the Z direction. However, is a time reversal breaking superconducting state. Okay, so now so I'm pretty much running to the wire. This brings me to the end of this talk. So just as a brief summary, the basic premise of what we've tried to do is we've tried to start from very simple toy models of asking about different types of heterostructure compositions and inquiring as one goes to small twist angles away from commensurate configurations, how engineering of the Moiré superlattice potentials gives a new route to engineering unconventional states of matter. So in the simplest case of a scalar potential, we've seen that for twisted bilayer MOS2, one can get a twist tunable anisotropic PXPY Hubbard model with interesting spin orbital physics. However, as one goes to the group 4 transition metal dichalcogonides, such as zirconium disulfide, one finds that this actually has to be extended from a scalar to a matrix valued Moiré potential, which gives rise to new physics. In particular, gives the ability to tune into an ultra strong spin orbit coupling regime, where really spin orbit coupling dominates the low energy dynamics, and combined with strong electronic interactions, if the band is flattened enough, can host a variety of correlated and topological states, in particular an interaction-driven quantum anomalous Hall insulator, and various states at fractional filling corresponding, for instance, to fractional quantum Hall states on a lattice. And finally, going into the third dimension via engineering the location of the charge puddles via the Moiré superpotential in such a manner that the charge puddles are not aligned between subsequent layers, this really gives twist control over the third dimension as well, sort of completing twist control of 1-dimensional, 2-dimensional, and 3-dimensional systems. So just a few comments on this. I think on one hand, it's even more interesting maybe to look at compounds such as hafnium disulfide, which has even stronger spin orbit coupling and has already been has already been studied by various groups in the untwisted mono and bilayers. However, also our study really focused on time reversal symmetry breaking instabilities away from half filling in a partially filled quantum spin Hall band. However, related and very interesting question that attracted a lot of attention a couple of years ago was the question whether you would actually have time reversal invariant correlated states of matter, sort of a fractionalized generalization of a fractional topological insulator. So in a sense, twisted heterostructures in the 1T coordination provide an ideal playground to try and search for time reversal, physics of time reversal invariant topological correlated states of matter. So let me just briefly acknowledge my collaborators. So first of all, Leda Xian, who's been doing tremendously difficult calculations of and ab initio characterizations of large supercell structures, and Dante Kennes, and as well as Amon Fischer at Aachen, who've worked out the superconducting instabilities of the three-dimensional stacking order and have done a lot of the theoretical modeling together with Angel and me that's been shown in this work, as well as Dominique Kiese, Michael Scherer, and Simon Trebst, who have done the mean field analysis on twisted MOS2 and shown the variety of spin orbital orders that this can arrange, as well as also Jin Zhang at the Max Planck Institute, who's been working on the three-dimensional twistronics. So thanks everyone for listening.
Great, thanks, Martin. That was a lot. That was super interesting. I'm sure other people have questions. I have first some simple question, which is going back to the zirconium sulfide. One of the questions I have about these 2D models is, when do you know whether you should just include a potential, or when should you include interlayer hopping, like interlayer tunneling?
Yeah, so the picture advocated here is, we're not, the basic band, the basic orbitals that we pick here. Oh no, sorry. Here we go. So the basic orbitals we pick are actually not orbitals that arise in the untwisted monolayer, but in the bilayer. So essentially, you should view this potential construction as something akin to like a K dot P expansion around the gamma point in the presence of a spatial alignment that changes, where the alignment of orbitals between subsequent layers change as you move across the supercell. So essentially, in principle, so we haven't done this directly from ab initio. In fact, Alan McDonald's group has done a similar study for MOS2 with an ab initio parameterization of the superpotential. You can really extract from looking at sort of the local energetics of the different local stacking configuration what that superpotential looks like. So essentially, the bilayer structure is already encompassed in the fact that these orbitals here are really the lowest energy valence band orbitals of the bilayer, not the monolayer.
Ah, I see. So instead of thinking of two layers with a twist angle, you're thinking of a okay, I think I see.
I think of an untwisted bilayer and then ask, well, what happens if I if I think about a spatial shift of the two layers with respect to each other, which generates a potential.
Hi, my team. Very interesting talk. I have two questions. One is related to the 1/3 Lafrance state. One is related to the Moiré. So maybe let me first ask the 1/3 Lafrance state. So I think in realizing the fractional quantum states, you need a spin value polarized band first, as you mentioned, right? Can you remind me why you increase the U prime, which the next nearest neighbor interaction will give you such spin very polarized band. Maybe you already mentioned, but can you remind me the argument here?
Oh, sorry. Why increasing U prime?
Yeah.
Right. So I mean, for the Laughlin, so fundamentally, actually, you already see this in the half-filled case. So the half-filled case. So for increase, actually, one of the more interesting consequences is that, okay, naively, so if I increase U, at some point, you know, my electrons can gain energy from just spin polarizing and hence paying no energy penalty U. So this flat band ferromagnetism for a local Hubbard interaction is well established. And just after critical U that exceeds the bandwidth gives full polarization. However, you see here that also, well, so by the way, the top line is not 0 U, it's finite, it's a small but finite U, to be fair. But as you increase U prime, you also find that you get a transition to a fully polarized state at a critical U prime. And sort of the underlying physics really is that of a topological Wannier obstruction. Yeah, so charge wants to localize because of strong Coulomb repulsion. So it wants to stop moving because the Coulomb repulsion will, you know, try and pack the charge in a particular pattern. However, the Wannier obstruction entails that these charge puddles can't be forming a localized, sort of a set of localized lattice orbitals. So the only way to circumvent this, sort of in a hand-waving way, is to break the underlying symmetry, which in this case is time reversal symmetry, corresponding, or, well, since it's a quantum spin Hall insulating state, actually also the U1 spin rotate, you want to spin polarize. So that's that's the intuitive picture coming from a Wannier obstruction. Now, if you're at a finite filling,
can I ask a question about what you just said though? Because the quantum anomalous Hall also has a Wannier obstruction, right? So that doesn't really help you localize charge, does it?
That's right. That's right. So the charge is, well, the charge is only localized because you're essentially packing it into one band, right? You're packing it into one of the spin bands, which is fully filled.
Okay, so it's still more localized than in the half-filled spin churn case, you're saying, even though it's not.
Well, so in the fully filled band, it's localized just because it can move. Like you're fully filling a band. Mm-hmm. So that's the only way. That's the only way for the system to localize its charges. If you had carriers in both the spin bands, since the fundamental orbitals that your interaction projects into are not localized, the system cannot just localize, say, spin up and spin down carriers by forming, say, irregular patterns of spin ups and spin downs. Mm-hmm. So the regular picture of the local moment formation doesn't work. When you polarize all your electrons into one species of electrons, you're just forming a filled band, so the electrons are immobile. Mm-hmm, mm-hmm. So, however, for the Laughlin state, you can also think that, you know, at some point, as you increase U prime, it just becomes energetically favorable for the system to open up a gap via avoiding electrons being in relative angular momentum states of low relative angular momentum, just like the pseudo-potential picture of the Laughlin state in the Landau level. And that opening of a gap saves energy, and that energy saving can cause the system to simultaneously break time reversal symmetry to open up this gap.
Yeah. So yeah, should I think of this formation of the Laughlin state as two steps? The first is that when I increase the U prime, I get a spin polarized band, and then U prime gives me a short range interaction that gives me a Laughlin state. Right.
That's right. So as I increase my U, yeah, you can think of this exactly. So as you have a finite U, essentially U causes the system to spin polarize.
Right.
And as the system is spin polarized, U drops out as an energy scale.
Yeah. So I understand
the energy scale is U prime that really dictates whether you can form an incompressible state.
Okay, so I understand the second step, U prime give me a Lagrange state, but what is the mechanism that U prime can lead to a spin polarized phase?
Wait, U or U prime?
U prime in the y-axis.
Ah, you mean, right, so there's two ways, right? So this, if you go in the horizontal direction, U will favor spin polarization because the system can just eliminate its energy penalty U by putting all electrons in one spin configuration. If you keep U vanishingly small and just increase U prime, at some point you can imagine that if you're thinking about the fractional quantum Hall state, the excitation gap above the ground state, sort of the lowering of energy, relates to U prime. So as you increase U prime very much, at some point it's energetically favorable for the electrons to both sort of simultaneously spin polarize and condense into a Laughlin state. So since this is a one-step direction and this is a two-step where you first polarize and then you condense into a fractional quantum Hall from the polarized.
Thanks. So my second question is about Moiré. So we know that in twisted bilayer graphene.
Sorry, could I ask a follow-up question about this? So it's like, look at the half filling, U and U prime played a similar role, and at one, because it's like both like increasing U or increasing U prime, we can get a quantum anomalous Hall effect. But at the 1/3 filling, like they played a different role.
Right. But at the 1/3 filling, if you have, say you have a finite U, so okay, in the half filling, both U and U prime are energy penalties for electrons trying to move trying to move or occupy the same spatial location in the same orbital. If you're at the 1/3 filling case or 1/6 filling in the spinful system, as you increase U prime, as the system polarizes, so if U prime is very low, if that's the dominant energy scale, then the system will just polarize ferromagnetically, because if you have spins in all one direction, then the energy penalty U prime is 0. However, U thanks. I mean you increase U and you polarize. You polarize ferromagnetically. Now, if you're in the ferromagnetic state, U drops out, but U prime will tell you how now all your polarized spins will try to arrange themselves. If U prime is 0, then essentially your spin polarized electrons will just fill the band up to the Fermi energy. If U prime is non-zero and it becomes larger, they'll try to arrange each other so they don't pay this repulsion. And at some point, since this is since if you're in the spin polarized state, you're in a Chern band, you can think of the electrons in the Chern band analogous to a Landau level. So the electrons have sort of a guiding center and a regular angular momentum that you can define by the guiding center coordinate. U prime essentially is somewhat analogous. Actually, you can make this analogy more explicit. We have an older work on this and other groups here too, in these papers down here. U prime essentially amounts to a V1 pseudopotential, which is an energy penalty for electrons to have 2 electrons to be in a relative angular momentum state differing by 1. So if they can't be in a relative angular momentum state differing by 1, they'll be in a relative angular momentum state of at least differing by 3, which is just the Laughlin state, which is the Zi minus Zj to the that's your Laughlin wave function. So actually here, U and U prime are very different. That's the reason why they're having a very different physics. Does that make sense?
Yeah, thank you.
Yeah, my second question is about, we know that in TBG, the strains and twist angle disorder affects the band structure a lot and affects the phase diagram a lot. So in your, you talked about the spin of the coupling and the 3D layers. So do you have any idea how the 3D layers of spin harmony, how will they increase or decrease?
Sorry, the 3D, this one?
Yeah.
We don't really have spin orbit coupling in this program.
Yeah, I know. So in 2D, the spin orbit coupling, the materials will have easier to have the twist angle disorder and the strains. Do you have any comments on that? It's on.
So the calculations that we did are fully relaxed calculations. So in principle, you allow for local domain relaxation. However, question. I think here the situation is a little more severe because now you can think about, twist angle disorder in the third dimension, where now you don't only have one twist angle, but you can have a twist angle disorder along each possible layer. And actually, I think that would be so we don't know, but that would be a very interesting problem to study.
Thanks.
I also have a question about the 3D stacking, which is just what's the difference between the A and A prime layers?
These are just the different stackings, the different relative positions of the transition metals in the two layers. So this is the A-B analogy and TMDs.
Okay, I see. So they're just translated.
So this is just showing here. This is just showing examples for alternating twist for graphene, for tungsten diselenide, and for HBM. So this is here.
So are the flat bands that you're getting in 3D really, are they different than having just separate 2D systems which are stacked and decoupled from each other?
Yeah, so the fundamental question is, are you just getting a trivial system where you move your orbitals so far away from each other that you don't get any hopping? Or not? Yeah. And I think sort of the naive answer is that actually this is true, and that's also true for all TMD-like systems. Like, unlike the magic angle conditions in graphene, in general twisted semiconducting systems, the low energy physics always arises from the fact that you're localizing charge puddles and you're changing the position and shape of the charge puddles and move them further away.
So then you would probably not expect like topological effects in the third direction, because you're kind of just localizing in the third direction here.
So that's a good question. So in principle, while you're localizing in the third direction, localizing just means that you're sort of separating out isolated bands that become progressively flatter as sort of the hopping in the third dimension, but also in the in-plane dimensions are quenched. So now I think the question of topology is still a question of what is the structure of the orbitals that form sort of these sets of bands. And you can envision, similar to the case of the TMDs, or a scenario where you have not one but two possible orbitals that make up a single Moiré charge puddle, and then think about spin orbit coupling giving you just the right interesting coupling between these orbitals that again can realize, say, a three-dimensional topological insulator or something more interesting. So I think really one would have to think about materials where these charge puddles are a little more involved in us. They might have multi-orbital character.
Yeah,
what are the consequences of that? Now the band gaps, of course, would be very small. So you would have topological gaps that are MEV energy scales.
Yeah, but that's kind of already happening in all the twisted heterostructures. I mean, maybe it's a little bit better, but it's still pretty small.
Exactly. And the question for 3D, I guess, is whether something similarly nice can happen that now this MEV energy scale competes with spin-orbit coupling, which is also MEV energy scale, giving sort of a combination of a flat band and still tens or MEV, tens of MEVs topological gap. But presumably one could also generalize this to, one could imagine having a vial system in which the vial semi-metal now appears, but in these dispersion quenched bands formed from the Moiré charge puddles.
Yeah, maybe that's more immediately feasible that it could happen.
Yeah, so I'm not really sure what would the system, what should the system have in order to do this? But presumably one could just essentially again do like a potential engineering analogy of like trying to take a vial semi-metal, a simple vial semi-metal model and trying to engineer a Moiré potential.
Yeah, I know there's a work from the Maryland's group. They proposed the 3D like the spiral twisting structure that may be relevant to the vial semi-metals.
Which group?
Maryland, CMTC.
Oh yeah, exactly. The SARMA, yeah. So
yeah.
Just I stopped sharing. Sorry, yeah, actually I had the reference in the slides. So what they're proposing is, so they're essentially looking at a continuously twisted structure and study this from a computing perspective.
Martin, I also have a question. Like in your earlier work, you guys also showed that you had bands which could be like localized in 1D and dispersing in 2D, in the other D. So is there anything interesting more to look at in that direction? Like now you have 1D flat bands. Can you? I don't know what kind of 1D states you'd be interested in studying. Or are you kind of not working on that?
Actually, this is one thing that we're, oh wow, okay, subtitles are on again. So this is one thing we're working on. So actually one interesting generalization is to ask, how does this work in a Dirac system? So you can think of a rectangular lattice Dirac system, an example, a possible example for this, although unclear how feasible this would be to engineer in practice, something like Graphene, where now if you have a rectangular lattice of Dirac fermions with a twofold rotation symmetry, then if you stack them on top of each other, you again get magic angle conditions, which now, however, have an intrinsic anisotropy. So you can get a different magic angle condition for the two different spatial directions. And this gives you sort of an interference tunable condition to generate sort of interpolate between the coupled wire and the two-dimensional limit. So I think the interesting thing would be then to look at something we haven't really explored yet, is to look at sort of what can we get out of such coupled wire constructions, and is there something something interesting and realistic one could propose?
Yeah, I mean, there's a lot of work in the topological community on wire construction. So is there any way to engineer wire construction? Yeah.
I mean, Charlie Kane pioneered a lot of the
I guess you're in the right place for that.
I think so actually it is one of the things we're discussing. One interesting thing would be to realize one of these constructions in a twisted model. And the idea, one interesting corollary of this is also, since these wires are spatially separated now on Moiré length scales. For instance, if you put such a system in a magnetic field, sort of the flux encompassed between sort of unit cells is fairly large, giving access to sort of a very unconventional large flux regime for, say, chiral wire construction.
Yeah, that's a really interesting idea. That was, previously people were thinking about making these out of actual wires, and it didn't seem like it would be so incredibly, maybe it's promising, maybe it's not. So this was definitely is a cool idea.
Yeah, if this order is under control, this should give you sort of a very regular pattern of one-dimensional.
That's very cool.
Yeah, by the way, Martin, so currently we're working following your previous 15 PRL paper on the ideal flat band. So we have a draft prepared and probably will publish soon. So do you have time to talk afterwards? So maybe you can talk in some details.
Sure, would be, yeah, sure, would be glad to.
Yeah, so I will send you an email to schedule a time.
Okay, sounds good. So actually, I'm free until 3 p.m.
Oh, okay. So today I have some appointments, but maybe some tomorrow or something. Yeah.
Sounds good. Yeah. So what are you studying? Just out of curiosity. So what?
Yeah. So you studied C equals to or higher ideal fat band. We studied C equals to 1 fat band. So
I see.
Yeah.
So it's is this elliptic theta function construction?
Yeah, elliptic theta function. We can, in this limit, we can have some precise duality between lambda levels.
Yeah, I'm curious to hear more about this.
Yeah. Thanks.
That's you and Jen.
Yeah, and Andy and other collaborators.
Great.
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 Well, thanks so much for organizing.
Yeah, this was super interesting, Martin. Thanks for giving us the overview of a lot of. It looks like you've been working on a lot of stuff in the past year, so it's great to catch up on this. And yeah, maybe we can chat soon with G about the other stuff. That would be really fun.
Yeah.
I just wanted to say hi. Sorry I was late. I had been listening to the Simons collaboration proposal from Alan McDonald and others.
Oh, great.
So we'll see. By the way, on my Zoom screen, there seems to be a voice to text thing. Are you seeing this?
I think that's my fault somehow. It's my, oh, here we go.
Well, I'm just curious. It's you know, it's not
somehow
great.
my PowerPoint automatically switches this on if I don't pay attention.
Yeah, actually, I like that. How do you turn that on?
There's a button, like if I right click on my screen, it says start subtitles.
Maybe I need to have
subtitles is sound to text.
Yeah,
that's very interesting.
Yeah,
it doesn't like physics very much. I think it's better for sort of regular speech.
Well, these translation things are tough, but no doubt it will get better. Yes. So look, I'm sorry, I have a slightly different question related to another thing the grant side of the Simons Foundation is doing. And that is, let's say, Chern-Simons theories generally. Right. And I guess my question is, you know, clearly, you know, there's a lot of equilibrium topological field theory stuff, which various people are doing. Some of which falls under the heading of Chern-Simons, right? But are there any interesting non-equilibrium effects? I mean, I seem to remember that some of your work with Angel could be put into that language of activating or deactivating topological terms by appropriate driving.
Yeah, that's that.
Or is that too much of a stretch?
No, so I mean, I'm thinking about, so how would I justify something like integrating out my electrons in a non-equilibrium setting? So I can, of course, okay, so I mean, there's two angles to this, right? So on one hand, there's sort of the Chern-Simons theory of a sort of the integer quantum Hall effect, where my effective action is the regular Chern-Simons theory. On the other hand, there's the Chern-Simons flux attachment for fractionalized phases.
Yeah.
Where I presume for energetic reasons that it's good for electrons to attach a flux, and then I integrate out my electrons and I get the transimus theory. So I guess in principle, one can still do this in a non-equilibrium setting, right? But one would have to justify why.
Yeah.
So the motivation is generally that in the flux attached theory, you just arrive at an effective theory of new Landau levels, where now a Landau level is fully filled, and one can make an energetic argument that this is hence a very stable configuration. In a non-equilibrium setting, if I have an energetic separation, if I have some energy scale separation between, say, an external, okay, maybe I'm thinking about, I'm thinking in the wrong way. Like if I were thinking, say, about a driven system, like if I drive in such a way that I still have an energetic separation with respect to my cyclotron frequency in the original system, maybe this could be justified to think about a dynamical Chern-Simons theory that arises.
Right.
From writing down like a Keldysh action to the flux attachment again and integrate out the electrons.
I think the Chern-Simons theory is intrinsically in 3 dimensions, so you have x, y, and t. So fundamentally, it's possible to have t. But what is the microscopic model that Chern-Simons arise for some non-equilibrium systems?
Like imagine you have a fractional, there was actually 2 or 3 proposals recently. Imagine you have a set of Landau levels, and you're driving this at frequencies that are detuned. Say the Landau level resonances are very sharp, so you have a perfectly clean system, and you're driving off resonant from the Landau levels. Then naively, if the driving is not too strong, at least for short times, there's again maybe pre-thermalization arguments that the system should just see this as some effective adiabatic perturbation. And then maybe one could still justify sort of the same procedure of doing a Chern-Simons construction. But in some sense, maybe that's not what you're asking, Andy, right? Because that would just give you some renormalized equilibrium Chern-Simons theory. So
yeah, well, I mean, I think there are several different things that I'm asking. But to start with, even we could generalize beyond Chern-Simons in that sense and just ask, are there ways, if we have systems with interesting properties that can be described by topological field theories of whatever sort, or theories with interesting both topological and non-topological excitations, like spin liquids or something. Is there a way to control these by non-equilibrium means? Is there a way to move across a phase boundary into a topological regime, for example?
Maybe this doesn't work. But one idea, like imagine, for instance, for a 3D TI, we have these theta terms that arise in the effective topological field theory, right? So, and one way of getting them is again sort of this procedure of essentially integrating out electrons coupled to a gauge field. Now, usually this is kind of like a linear response construction, right? So it's essentially trying to devise a theory for, like, if I have a weak electromagnetic perturbation, I get now an E dot B term that couples my electric field to a magnetic field coupled by a theta term. So would it be sensible, like if I did this in, say, a non-equilibrium setting and non-perturbatively, I should get some other contributions which should give me a coupling between my field and my theta term. So for instance, I could imagine like there should be some, a term in my field theory that will change my theta term as a dynamical variable as a function of the driving field.
Yeah. Yeah, so that's sort of the thing I had in mind. And I think what you're saying is that this is at least not something that anybody's thought about, and possibly something that would be quite hard to realize.
I mean, one idea that I had that, again, and I don't think it's very physically motivated, but you can have different topological phases that like you can condense quasi-particles to get between different topological phases that have gapped boundaries with each other. And I guess one thing I was wondering was, could you condense this thing? Could you have like a quench, like a, yeah, could you condense this thing as a function of time? And is there some interesting dynamics of entanglement that are there? But I mean, I haven't actually thought about this. It's just some vague words that I've written down on some vague proposals.
Yeah.
In the past.
Right. Well, but I always wondered what would happen if you just by whatever means did a quench into a topological phase.
I think in quench inland levels, I know in quench inland levels, I know some examples. So suppose you change the metric of some Graphene state suddenly, and you see how the system evolves, and people find that this is related to the graviton mode at long wavelengths, and they can precisely calculate the period of that and match well with numerics. This is the only example I know about quench dynamics. But I think probably you are saying different things like periodic driving or not.
Well, they're different. I mean, there's. I was just trying to think if there are any non-equilibrium connections.
Yeah, I mean, and also lately people have been classifying flow K topological phases.
Right.
This is a little bit different than applying a driving field to an existing topological phase, I think.
Yeah, but there are certainly people have talked about Fluke topological phases. So you could ask what are their properties, and you could ask what happens if you turn them on and off.
Yeah.
Yeah, so I wonder if there's anything interesting there.
Yeah, so so there are different types of transients. As I know, one is the U1 abelian gauge transients, which is the most usual one. Another is related to the geometric degree of freedom of the, for example, Flatiron quantum Hall. That's the related to the connection field. If you think of connection field as a U1 gauge field, this is a new type of transients. So the quench dynamics is more or less based on that degree of freedom. So I think this geometric degree of freedom should also exist in other systems because it's fundamental.
What's the observable of this? Is that like some Hall viscosity or something?
Yeah. Right. Hall viscosity is the consequence of this geometric transients term, and the thermal Hall related.
Right. Okay. Thanks. Look at this is interesting. I may come back to you. It depends. My motivation actually is just that they're organizing a little symposium on Chern-Simons effects, which is driven by possibility of using these cosmological telescopes to see some kind of birefringence in the cosmic microwave background that might or might not reveal the existence of some kind of Chern-Simons term in the inflation field.
So it's not a condensed matter.
Well, so I just am trying to think of condensed matter things that are interesting.
Okay.
That could also be part of this, particularly if they're talking about funding research in this area. And a lot of the equilibrium Chern-Simons stuff, to my mind, has been done basically.
Right.
I don't know what the new questions are in our world. So anyway, that was my motivation. That's so all right. Anyway, thank you very much.
Like cycling back to this, I mean,
yeah.
Is it really? Oh, no. Okay, sorry.
No, go ahead.
No, I mean, is it really so unrealistic to think? I mean, essentially, maybe this has already been proposed, just not put in this language, like a sort of non-equilibrium controllable axion insulator.
Yeah.
Just thinking about So an effective field theory of an axion insulator that's pushed away from equilibrium.
Yeah. Well, I mean,
no, that's not Chern-Simons, but
yeah, but we could say topology more generally.
I think that when we were talking to David Vanderbilt's student Nicodemus, I think that I vaguely remember him mentioning something like this. And now that you're saying it, it sounds like exactly something that David would be thinking about. But I don't know if they have a paper on that or if, yeah, I don't remember.
Yeah, well, maybe I'll ask David. But
so David Reitman?
No, Vanderbilt.
Oh, Vanderbilt. So.
Yeah, but I always wondered, these topological terms imply something about gauge fields and so on. And in one sense, I can't continuously tune them away, right? They have coefficients which are just numbers, but on the other hand, there should be some control parameter that turns this thing on and off, and that shows up somehow in, finite length scale dynamics of the theory.
Right.
So how it knows? Is it a matter of, if I quench into a topological phase from a non-topological one, I get a sea of, various generalized vortex and anti-vortex configurations that anneal each other out, or do I have like a term with that my topological theory has a gauge symmetry, effective gauge symmetry, which is broken in the non-topological phase? So there's something like a mass term for a gauge for a field which becomes a gauge field as I tune some parameter because its mass goes to 0 or something.
I mean, it seems like there could be multiple, multiple types of transitions. One of them would be a mass term condensing stuff, which would take you between like different sorts of compatible topological phases. And then it seems like there's going to be other transitions like between topological and trivial, which probably require some gap closing phase transition. So you'd need to like then that's a bit more, you need to have a more complicated model.
Mm-hmm.
And this effective theory can be compared with numerical results on microscopic Hamiltonians.
Yeah, right.
Yeah. For the fractional quantum Hall, I know some works, and if I can send you if you are interested.
Yeah, that would be fun.